Good afternoon to everybody, and welcome back to our IAC seminars series. If it's okay for you, we suggest to continue in English just for a better online diffusion of the contents. But if not, please tell me so we can continue in Italian. Okay, today the speaker is Dr. Angela Monti. It's a really pleasure for me to introduce Angela, whose first experience at CNR has been in 2022, when she was a PhD student in mathematics. Just very recently, more precisely on last April, she started her activity in our institute, precisely at IAC, placed in Bari, as a temporary researcher on the PNRR project, National Biodiversity Future Center. She attains this role thanks to her various skills. Among them, for sure, we can recall qualitative study and numerical approximation of population dynamics, mathematical models for patterns formation and intermittency, and model order reduction techniques. On all these topics, she can exhibit a scientific production of national and international impact. We again welcome to Angela in our institute. We wish you a pleasant and fruitful activity in our institute, but especially many thanks from all the organizing committee for accepting our invitation to take this presentation. Now I leave you the floor, and for everybody, the title of the talk is Population Outbreaks in Host-Parasitoid Models, the role of on-off intermittency. Please, Angela, and thank you again.
And good afternoon, and thank you for the invitation. It feels like home for me to be here in CNR. And today I will talk about my last two papers that are a joint work with Fasma Diele and Carmela Marangi here at IAC in Bari, Antonello Provenzale, and Deborah Lacitignola from Università di Cassino and del Lazio Meridionale. The idea is this one, sorry, I switched in Italian, but I continue in English. And we want to study host-parasitoid systems, and first of all, I will show you the motivation, why we are interested in such systems, and in particular, I will focus my attention on the Beddington-Free-Lawton model. So let's have a look here at some ecological interest in studying the interactions between parasitoid and hosts. In particular, because from an ecological point of view, the parasitoids can be used as a pest control or also as biological control agents. And from a mathematical point of view, we are interested in this interaction because they allow us to study a variety of nonlinear dynamical behaviors. Our model is the Beddington-Free-Lawton model, is a time discrete model of two equations where the unknowns N and P represents the host and the parasitoid biomass. We have different parameters in this model. In particular, we will focus our attention on delta, that is the grazing intensity, R is the host growth rate. Then we have B, that is the growth rate of the parasitoid, K is the carrying capacity of the host, and A is the searching efficiency. We can perform change of variables, and we obtain this model here where we have the second equation that does not depend on any parameter, whereas the first equation depends on the delta, R, and the K, that is a rescaling of the carrying capacity of the host. So the idea is how can we introduce an environmental variability inside of our model? First of all, we can vary some of the parameters in the model in a stochastic way. So what is known is that the environmental variability is important for the coexistence theory, and it can be viewed as an unpredictable spatiotemporal fluctuations that give rise to different changes. In particular, environmental variability can modify the degree of the competition between species. It can also change community compositions and the coexistence between species, but also it can have an impact on the population parameters. And we can see these in external factors like the change of weather, the availability of food, the occurrence of diseases, but also competition from other species. So population outbreaks, in some sense, are bursting behaviors that are caused by environmental variability. And one of the way we can explore the role of environmental variability is by stochastic perturbation of parameters. So what we do in this talk, I will show you, first of all, a random variation of the grazing parameter delta that is well known in the literature, but then we focus our attention on the random variation of the host growth rate. So we study from a mathematical point of view the dynamics that is behind the on-off intermittency, and then we propose to substitute the stochastic driver with a deterministic chaotic system that represents in some sense the dynamics of the environment. And we will show in both cases, so both in the deterministic framework, but also in the stochastic framework, that the reactivity of free-parasitoid fixed point will be a necessary condition for the occurrence of on-off intermittency. The concept, the notion of reactivity will have a different sense in the stochastic or deterministic frame. So first of all, we consider delta, that is the grazing parameter, and we allow a variation in time according to this variable epsilon t that is a random variable with the normal distribution between 0 and 1. So this variable here can attain a minimum delta and a maximum that is capital D. Our system is this one, so only this parameter is varying in time, and we have only one fixed point, that is the extinction fixed point. So we want to study the stability properties of this fixed point, and we consider the Jacobian matrix evaluated at the fixed point P0, but pay attention because this matrix here depends on time. So we can perform the product of all the matrices to relate the perturbation at time t to the perturbation at the initial time, and the stability of the linearized system is determined by this long-term behavior that is given by the limit when t goes to infinity of 1 over t and the logarithm of this guy here, that is the In some sense, it measures the rate of amplification at time t with respect to the initial perturbation. And if we use a Euclidean norm of vectors, this guy here is given by the spectral norm of the product of these matrices, and this given by the maximum, the largest singular value of this matrix here. So we can use in the statistical framework the law of large number, because here we have this limit of the mean of this variable rho, and we can compute this limit as a phase space average. So we make use of the law of large number and obtain the stability curve that is depicted in this plot here, where we can see in the parameter space delta capital D, that is the range, the minimum and the maximum amplitude of the grazing parameter, and we can see the stability curve. What is well known in literature, that we can choose parameters here just above the stability curve and see the occurrence of an off intermittency. So let's have a look here. We have fixed all the parameters except D, capital D, and in the left here we choose parameters on the curve, on the stability curve, or just above but very close. And on the right, we are far enough the stability curve. What we can see, this is the temporal time series of the host population, and we can see here the occurrence of on-off intermittency that is in some sense quiescent phases and then bursting peaks here. On the right, we have chaotic behavior. So this is what we can see, but we can also quantify in some sense on-off intermittency, and we can characterize intermittency by using this statistical tool that is the kurtosis. We can compute the kurtosis of the time series with this formula, and the kurtosis is able to detect extreme deviation. So if kurtosis is equal to 3, we have a normal distribution. If kurtosis is much greater than 3, then we have the occurrence of an off intermittency. And as for regards this plot here, we expect an off intermittency for these 3 cases, and not on-off intermittency here, and this is confirmed by the value of the kurtosis that in the first 3 cases is much larger than 3, and for the last one, no. So the idea is that we want to study the random variation of the host growth rate. So we fix delta equal to 1 and consider the random variation of R. In this case, we have 2 fixed points. First of all, we have the extinction fixed point, but it is not useful to study because it is always unstable, since lambda t, that gives the long-term behavior, so the stability properties, is always greater than 0. So we switch on the free-parasitoid fixed point, and we study the stability properties of this point here. And pay attention, because in this case, the Jacobian matrix is triangular but not diagonal. So if we want to study the stability properties, is not useful to compute the spectral norm and so the largest singular value of this matrix, and we use this lambda tilde t that is different from that but has the same sign, and in particular we compute, instead of the largest singular value, we compute the maximum eigenvalue of this matrix here. So we have 2 eigenvalues, the product of 1 minus Ri and k to the power of t. And if we suppose that this relation holds, we have the stability curve, and in particular, we want also to focus our attention on another notion, that is the reactivity. The idea is that we know that above the stability curve, we have the occurrence of on-off intermittency, but we wanted to explore if the reactivity of the fixed point plays a role in the occurrence of on-off intermittency. So first of all, I want to recall for everybody what is the reactivity for a time discrete system. In some sense, we have to consider the perturbation of time t. We can relate it to the perturbation of initial time. And we have here this H that is the product of all the Jacobian, because we have the Jacobian that depends on time t. Now, the amplification envelope, phi t, gives us the rate of the perturbation at time t. So how much we are far from the initial perturbation. And if we consider Euclidean normal vectors, this is given by the spectral norm and so by the largest singular value. Now, the resilience gives us information on what happens to the long-term behavior of the fixed point and is related to the amplification envelope, whereas the reactivity gives us information on the transient behavior. So the idea is that a fixed point is reactive when the first time step after the perturbation, the logarithm of the amplification envelope is greater than 0, and so when the largest singular value of the Jacobian matrix is greater than 1. But now, how we can, in some sense, say what is the reactivity of a fixed point when we have a matrix that is changing in time, but in particular depends on parameters. So here we have written the largest singular value of the Jacobian matrix, but clearly this depends on epsilon, that is our random variable that can be different in any simulation. So we want to avoid the dependence of the reactivity on the first epsilon chosen in the simulation. So we say that the fixed point is reactive when the mean, in some sense, is greater than 1. And we can compute the mean by using the phase space average. So here we have the formula of the reactivity curve. And in this plot here, we are in the parameter space R, capital R, that are the minimum and the maximum amplitude of the host growth rate. We are changing the parameter C. Here we have 0.1 and 0.01. And what we are depicting here is the value of the kurtosis for the host population. In red, we can see the stability curve. In green, we have the reactivity curve. And here we have the numerical evidence of the fact that just not only above the stability curve, but also below the stability curve, but where the fixed point is reactive, the kurtosis is much greater than 3, and so we have occurrence of on-off intermittency. So this is a numerical evidence of the fact that the reactivity of the fixed point is a necessary condition for the occurrence of on-off intermittency. And this plot confirms our supposition, because here we are fixing the parameters K, C, and R, and we are varying capital R in such a way that we are just on the stability curve, just above the stability curve, and we have on-off intermittency, but also below the stability curve, where the fixed point is stable but reactive. And the occurrence of on-off intermittency is confirmed by the values of the kurtosis that are much larger than 3 in any case. So, after all, in another work with Deborah Lacitignola, we have explored the use of a deterministic driver. to obtain on-off intermittency. So some differences with respect to the stochastic framework, what we use as a deterministic driver. Here, delta, the grazing parameter, is varying with respect to epsilon, and epsilon varies in time according to a deterministic law, and we have chosen the most famous chaotic, that is the logistic map. So our system now has three equations. The first two are the Beddington-Free-Lawton model, and the third one gives us the evolution in time of delta according to the logistic map. S is the parameter in the logistic map. Now our system can admit 6 fixed points, 2 extinction, 2 free-parasitoid, and 2 coexistence. So the occurrence of an off intermittency in the deterministic framework is related to the so-called blowout bifurcation. In order to see blowout bifurcation, we need a response system and a drive system. The response system determines the number of invariant subspaces that are the quiescent phases, and in this case is given by x equal to y equal to 0, that is in some sense the extinction fixed point, and the drive system determines the dynamics of the chaotic attractor in the invariant subspace T, and in this case is given by the logistic map. The question is, when a chaotic attractor in the invariant subspace T is also an attractor in the full 3D space. So this depends on the sign of the largest transverse Lyapunov exponent that can be computed in this way. So first of all, we consider an infinitesimal perturbation transverse to T. We can relate the perturbation at time t plus 1 to the perturbation at time t according to the Jacobian evaluated at time t. And then again, we can compute lambda t, that is the largest transverse Lyapunov exponent. Again, we have this limit here, but now we are in the deterministic framework and we cannot use the law of large numbers, so we cannot compute this as a phase space average. Now, what we have is that if lambda t is less than 0, then the chaotic attractor in T is also an attractor in the 3D space. And if lambda t is greater than 0, then trajectories that start in a neighborhood of T then are repelled away from it. And the occurrence of blowout bifurcation is given when lambda t moves from negative to positive values. In this plot here, I fix the value of the parameter S in the logistic map in order to have a chaotic driver. And we consider how lambda t, so the transverse Lyapunov exponent, is varying with respect to capital D, that is the maximum amplitude of the grazing intensity, for different values of D, here equal to 0, and then increasing these values. We can see that we find a critical value when lambda t is moving from negative to positive values. But if we increase the value of D, here D is equal to 0.2, then no blowout bifurcation can occur because lambda t in this case is greater than 0 everywhere. So we fix D equal to 0, so the minimum of the grazing intensity is 0. And we can see that again, if we are very close to the critical value where the lambda t, so the Lyapunov exponent is moving from negative to positive value, that in some sense gives us an interpretation of the stability of the fixed point, then we have occurrence of on-off intermittency, this blowout bifurcation in the deterministic framework. And this is obviously confirmed also by de Courtos's values. And if we consider D different from 0, we can observe this curious behavior of the parasitoid population, because in each case here, the parasitoid population remains equal to 0, whereas on-off intermittency occurs only for the host population. Here, if we increase the value of D, we can see that if a chaotic behavior occurs for the host population, then also the parasitoid population survives and has the same behavior, chaotic behavior. So for all the plots that I have shown just in the previous slides, we have the confirm of the occurrence of blowout bifurcation by the kurtosis values. And here, for the last example, the kurtosis is 1.5, that is less than 3. So no on-off intermittency, as we can see here. Now, the idea is that we want to study the reactivity also in this deterministic framework, and then we consider the Jacobian matrix evaluated at the fixed point 0, 0. Also in this case, it depends on the initial value that we consider for the logistic map. Now, epsilon 0 is the initial condition of the variable that evolves in times according to the logistic map. Now, the reactivity is important, but the classical notion of reactivity gives us information. In some sense, if a fixed point is unstable, then it is reactive. And if it is stable, it could be reactive or not reactive. But if we compute the reactivity in the classical sense, then it could happen that a fixed point is unstable but not reactive. So we need to change the notion of reactivity, and in some sense extend this notion in this framework. So we propose to consider a long-term reactivity. We say that a fixed point is a long-term reactive if the limit, when t goes to infinity, of 1 over t of the sum of all the logarithm of the singular values of the Jacobian matrix is greater than 0. Now, first of all, if the Jacobian matrix does not depend on time, we recover the classical definition. So this is effectively an extension of the classical notion of reactivity. Moreover, if we use the properties of spectral norms, we obtain that the Lyapunov exponent is less than the long-term reactivity. And this implies two facts. In particular, if the fixed point is unstable, so this guy here is greater than 0, then this is greater than 0, and so the fixed point is long-term reactive, whereas if the fixed point is stable, it could be long-term reactive or not. Now, we want to plot the stability and reactivity curves in the parameter space D, capital D, and look at the value of the kurtosis of the host population. In this case, we can observe that the occurrence of blowout bifurcation is just above this critical curve that is the stability curve that coincides with the reactivity curve. So this we have already explored this fact, and the case of varying delta in time does not give us information about the role of the long-term reactivity. So as for the case of a stochastic perturbation, we consider now the variation in time of the host growth rate. In this case, we have two invariant subspaces. The first one is given by the extinction fixed point, and the other one is given by the free-parasitoid fixed point. So S0 is always unstable, and we switch to the stability of S1, and also in this case, we can compute lambda tilde by making use of the largest eigenvalue, the maximum eigenvalue, and not the largest singular value, because the matrix here is not diagonal. And here we can obtain the longer-term reactivity curve that we now depict. In this parameter space, what we have is for different values of K, that is the carrying capacity of the host, we depict in red the stability curve that is given by the largest transverse Lyapunov exponent, and in green the long-term reactivity curve. And the kurtosis of the host population gives us evidence, numerical evidence, of the fact that also in the deterministic framework, the long-term reactivity is a necessary condition for the occurrence of an off intermittency. In these plots here, I'm showing you, here we are just above the stability curve, so we expect on-off intermittency for the host population. Here we are below the stability curve, but the fixed point is long-term reactive, and also in this case we have the occurrence of an off intermittency. So in conclusion, what I'm showing in this talk is first of all the occurrence of an off intermittency in a randomic scenario. And this work with Antonello Provenzale and Fasmadiele, we have shown that the onset of an off intermittency can occur in the reactivity region of the free-parasitoid fixed point. Then, with Deborah Lacitignola, we have also explored the environmental variability as a deterministic aperiodic driving process. And so we have shown that the stochastic forcing is not the only way for on-off intermittency. And in both cases, in the deterministic and stochastic framework, we have shown that the reactivity or long-term reactivity is a necessary condition for the emergence of on-off intermittency. In the future work, we are focusing our attention on a global stability study of the fixed point. And also we are interested in changing the deterministic driver by using other discrete map. And here are some references, and thank you for your attention.
Well, first of all, many thanks to Angela for her very kind and interesting presentation. Now, are there questions or comments? Okay, I have a question for you, Angela. Okay, the question is, you have analyzed one host parasitoid system, but what happens if you consider a number n greater or equal than 2 of interacting host parasitoid populations?
Okay. For time reason, I didn't show you this result that you can find in the paper with Fasma Diele, Carmela Marangi, and Antonello Provenzale. And we explored what happens if we have different host parasitoid systems that interact between each other. And in particular, we have shown that even if only one of these systems exhibit an off intermittency because of a stochastic perturbation of parameters, the other systems, the other populations that have fixed parameters show on-off intermittency because of the relation between each other. So we have used the network framework to show the evidence of on-off intermittency also in other populations.
Okay, sorry, Angela, I have a question too. Okay, in your numerical results, on-off intermittence affects only host population, while extinction of the parasitoid population is observed. So my question for you is the following one. How you can explain this from an ecological point of view?
Okay, the idea is that the study of interaction between host and parasitoid can be useful for use parasitoid as pest control or as control biological control agents. But if in the case of an off intermittency here, we have seen that when the host population exhibit on-off intermittency, then the parasitoid is always zero. And this, in some sense, it means that the peaks here of the host population are not enough for the existence and the precision of the parasitoid population. So in this case, we can think about how we can use the parasitoid to control pests if they go extinct. And here we have found that there is a critical value of D that is, in some sense, the minimum amplitude of the grazing parameter that can give rise to the persistence of the parasitoid population. So from an ecological point of view, it is we have to control the grazing parameter in order to persist the population, the parasitoid population.
I see another question. Okay, from Roberto Manalini. Do you think that a continuous model would give different qualitative results?
Maybe the study will be different for continuous model, and this will be the next step for us to study a continuous model that gives rise to the same behavior, and maybe it will be different from a mathematical point of view to represent the occurrence of this intermittency, but the qualitative result may be the same. Oh. Okay, or maybe are they already explored in literature?
Okay. Are other questions or comments? Okay. If not, we thank again Angela for her presentation, and we will see on next seminar. Okay.